So far, we have learned that the Black-Scholes model is not able to calibrate to implied volatility smile or skew. It's because a simple volatility parameter sigma is insufficient for the calibration to multiple strikes. In this lecture, we learn how to improve that model and perform, let's call it a simple trick by including jumps to the model, such that we are actually able to improve the Black-Scholes dynamics and introduce extra flexibility that allows us to calibrate to more than one single strike in the implied volatility shape. In this way, we actually move from diffusive model to so-called class of jump diffusion model. Let's take a look at the content of today's lecture. First, we will start with the discussion how to include jumps in the stock process. So it's basically how to, if we consider Black-Scholes model, how to actually include a jump and what is jump, what is the definition of a jump, and how to think of it once we think about a process and its discontinuous features. Second point, I will show you how to perform a simple implementation of a jump process in Python. Once we talk about the dynamics of a model of a process for a stock, which includes jumps, we also need to learn how to calculate and how to deal with the jumps once we have a ethos lemma. So as we have seen before, once we define an arbitrage-free portfolio or replicating portfolio for an option or to determine the option value, we have to perform ethos lemma in order to find the dynamics of the portfolio. This means that we, at some point, we also need to know how to deal with jumps in a process. So if we include jumps into dynamics, how to deal with that by application of ethos lemma. Next point, which is also very important, is that I've already repeated it multiple times. Once we deal with a stochastic process for stocks, we know that certain quantities, especially discounted future stock value, discounted to today, has to be martingale. So this puts some conditions on the drift of a ratio of a stock divided by money-six account. This means that we need to know how to take into account jumps in the process to make sure that our model is still under Q measure. Once we have a jump in a model, we don't have any more pricing PDE, partial differential equation, but we have to deal with a PID. So inclusion of jumps into pricing always introduces additional integral term. Essentially, this integral term, it is additional integral that it will be present in a pricing PDE. In this point, we will discuss what kind of distributions we can choose for jumps, and what is the impact of those distributions on different implied volatility shapes. In the next point, I'll show you how to use expectation, iterated expectation, so-called tower property of expectation, to calculate certain complicated expectations. Expectations once we deal with jump processes. This will be very handy later once we talk about derivations of characteristic functions, which will be actually next point, the final point of today's lecture. Characteristic function for jump processes. Characteristic function, we already have seen definition in the previous lectures. Characteristic functions is a kind of a model you can think of that is going to be used later once we talk about the calibration of those jump diffusion models. Remember that at this point, once we include jumps, we essentially also include multiple additional parameters to the model regarding the jump intensity, jump sizes, etc. This means that our model, instead of having one free parameter sigma, will have multiple parameters. Of course, depending on the jump distribution that will be it will be possible for us to choose. This means that once we have model of multiple parameters, we have a problem that we need to calibrate our model. And for that reason, we will use characteristic function that will be inverted using Fourier transformation that we will learn in next lecture. As we have already discussed earlier, the Black-Scholes model is not a perfect model for pricing options, especially if we think of calibrating in pricing options that depend on multiple strikes. single volatility parameter is not capable of calibrating more than one strike value if we think of calibration to European option prices. Now we will talk about extending of the model to jumps. Of course, once we talk about jumps, it's not only about having more parameters and fitting European option prices, but the dynamics of the model should also resemble the one that we see in the market. And in this slide, I have prepared a stock of KLM. As you can see, the behavior of stock is not as it was for the geometric Brownian motion. As you remember, geometric Brownian motion, it's an exponential process, so the paths have tendency of going exponentially on average, and of course, depending on the volatility, they can move up and down. But the behavior, the paths itself, they are diffused because they are driven by Brownian motion. So they're driven by the Wiener process, so they are continuous and they don't reveal any jump patterns, jump-like patterns. If you look, for example, at the KLM here, we could see that if we zoom in, you can see multiple jumps that would not be able to be explained by the geometric Brownian motion process. As you can see, it's one here. There are multiple jumps here. You see 1, 2, basically every month, every quarter, there is significant either drop or rise of the process. And that cannot be well explained by geometric Brownian motion. There are multiple reasons why the jumps occur. It could be related to the market fluctuations, so some unexpected events. But often, if you look at the jump process or you look at the paths from a stock, it's often also associated with dividend payments. So this is very important to keep in mind. If we have a jump, if you have a stock which has a one particular date at which it jumps, and that date is associated with a payments of dividends, that's not real jump because dividends are known, so that could be easily extracted. However, as you can see in this particular example, stock has jumps on multiple occasions, so that's very unlikely that those events, those jumps happen exactly at the number of dividend dates, because that would mean that this stock is paying dividends on a very frequent basis. Also here, the magnitude of jumps tells you that this definitely is not related to a dividend, because this is a substantial, almost 100% or more than 100% in this case, jump of a stock value within a very short period of time. Of course, the reason why stock is jumping, why it jumps, there are multiple reasons. Could be political. For example, there is a political conflict, or for example, there is a problem in delivery of commodities that stock depends on. So in the case of KLM, we could, for example, think that KLM is using a lot of oil. So if there is a big jump in the oil prices, that would also mean that the KLM would be affected by that, especially since oil is one of the biggest costs, or the most important cost for the airlines. Also interesting jump is the one which we see here, is that in a very short period of time, jump went up, so we had a positive jump, and immediately, or very short period of time, the jump happened downwards. So it could be with conflict with unions, which was resolved immediately, or some other reasons. So as you can see, if you like to model this behavior with a geometric Brownian motion, that would be very difficult. For that reason, we need to think of a process which includes this jump phenomenon and allows us to better fit not only to the paths of the process of the stock, but also allows us to fit to multiple strikes if we consider option pricing. So let's take a look at the class of jump models, processes that we will be considering. We will be focusing on a levy-based models. So those are the jump diffusion models. So diffusive part, you can think of the Brownian motion, and a jump part, which is included to the diffusion part. They're very attractive because they can explain jump patterns exhibited by some stock. So this is what we have just seen in an example of a KLM stock, when the jumps happen on some random moments that we cannot really predict. The presence of jumps has been observed in the market. In the example that we have discussed, we could not really associate those particular jumps with particular market events, but we could expect that there will be huge jumps if we have a market crash, like we had in 87, we had 2000s, this is dot-com crash, 2008 when we had a mortgage crisis, 2020 when we have when we had Corona crisis. Jump models are realistic when pricing options comes to maturity. So this is what we will also see later once we'll be looking into coding exercises, that um, jumps allow us that allow for better calibration. If we think of a smile, so maybe you remember, if we have a short maturity, the smile is very peaked, and that could be well explained by inclusion of jumps in the model. Of course, the question is to which extent somebody is interested in the pricing of short maturity options. So typically, if we think of a calibration of a model in order to price, so let's say some exotic derivative, typically we'll be interested in a longer maturity. So then short maturity options are not so much of interest. How to think about it? If you have a contract, which is rather complicated, exotic hybrid derivative, for example, and you like to price it with a model, or you like to calibrate the model to the market, you always calibrate to the instruments that they are used to hedge derivative. So if you have a derivative, let's say of maturity of 10 years, it's very unlikely you'll be hedging with instruments which would expire in coming days or coming weeks. So then you have to have there is a correspondence between the target instrument, the target derivative you want to price, and also instruments that you want to use for hedging. Another important point is that jump processes are superior to the Black-Scholes, especially if you talk about the heavy tails. So by inclusion of jumps, the tails are not anymore as, let's say, flat as they would be if we would have a jump included in a framework. So then the assumption about the normality of returns, which is unrealistic assumption, doesn't hold. So if we have jumps in the framework, we can improve the properties of jumps, especially if we compare to the stock behaviors in the market. Empirical densities are usually too peaked compared to the normal density, the phenomenon known as excess kurtosis. So as you maybe remember, when we talk about log returns or returns of a stock, we would consider this quantity, delta t plus, this would be minus st divided by st. In the case of a Black-Scholes, we would expect kind of bell-shaped returns. However, if we look at the returns from the market, or we look at the returns from some stocks, it's often those returns are much more peaked. And they are basically much more fatter tails. So it's a fatter tail here in the tails, and very much peaked, much more peaked that normal distribution could fit. So this is something to keep in mind, and this is confirmed by empirical studies. And the final point here is that with parameters we can control kurtosis and asymmetry of the log return density. So we can, if we have additional parameters which corresponds to jumps, we can specify whether the jumps happens in the low end. So for very small jumps, we have many small jumps, or we have large jumps. And depending on whether we have a small or large jumps, we could control tails, and could be left or right tail. And that could facilitate us with a better fit to implied volatility smile or implied volatility skew. So as you can imagine, if we have large jumps, then that would generate higher prices, or stock could go much higher, and that would generate that affect implied volatility smile in the far end. So let us now build a process which would include a jump. So we consider under the log transformation, so under the log space, we consider the following dynamics. We have a dxt equals to mu dt plus sigma dw under measure p t. So we have basically this part is just arithmetic Brownian motion. It's normally distributed. So it's a diffusive part. And plus we have a j, which is a stochastic variable, which is basically describes the magnitude of jump. Then we have a second process, dxpt. And this is also, it's a stochastic process. It is not Brownian motion. It is a process which is, first of all, uncorrelated to Brownian motion. And this process represents number of times we have a jump. So it's a count, you can think of a counting process. So at even time, you ask yourself or check, was there a jump or not? And if the jump happens, it happens with this magnitude. Let us look at the definition. So the common way of describing this process XPT is by modeling this jump process with a Poisson Poisson process. Before we describe a process, we need to describe the random variable Poisson random variable. XP counts the number of occurrences of an event during a given period of time. So like in a jump process, you would say, if I have a given number, given time frame, how many times the jump happens. So you basically count how many times the event happened. And then we have the following probability associated with that. So it's a probability that xp is equal to k. So we have a probability that we have k jumps is given by the following expression. So it's xi pk exponent of minus xi p. And then we have, you can see that there's actually one parameter that you can control. It's essentially the average intensity you can think of jump occurrences. Of course, you see right at this point we have just jump the Poisson process is the Poisson random variable, so we still have to link it to the process, and that will happen in the next slide. This pattern, or actually you can see that this construction is very much based on what we have learned so far. So we have a diffusive part, so the part which moves very smoothly, and we have a part which represents jumpy behavior in the stock movements. Let us now define the Poisson process. So the definition of Poisson process is very similar to one that we have seen for Brownian motion. It has initially it has a zero value. This means that at time t0, once we start, we have no jump. Second point is that we have independent increments. So as you can see, we have a time grid. T0, T1 is independent of T1, T2, and so on. So if you have a time frame, all these intervals, they will be independent of each other. So if you have increments from here to here, from here to here, those increments are independent as long they are not intersecting. Once they intersect, they of course they are not independent anymore. And the third assumption is about the distribution. So if we have 2 points, so we have a point S and we have S plus T, the number of jumps that we have a probability that we have exactly K jumps in this interval is given by Poisson distribution. So this is how we can think. XPT, so already as mentioned before, it's a counting process. The number of jumps in the time period of length of t. So you can see that the length between from s to s plus t is exactly t. Equation 1, we can also conclude that it confirms the stationary increments. Since increments depend on the length of the interval and they're not depending on the initial value. XP, so xi p, is the rate of a Poisson process. So it tells you about how many times the average amount of number of jumps that we have in a specified period. Okay, probability that exactly one event will occur in a given small, possibly small time interval dt. Here, as I already mentioned before, we use dt, but proper notation would be delta t, which is a discrete version. So what we do is as following. The probability that in these intervals with s plus dt minus x p s is equal to 1, following the definition from previous slide, it is equal to the following expression. So xi p dt, which is the time interval, so between s to s plus delta t minus s is delta t, and this is equal xi p dt, and we have a small o dt. On the other hand, we can also ask ourselves, what is the probability that exactly 0 jumps will happen in a given interval? And for that, we have, as you can see, it's a very similar expression with 1 minus xi p dt and with a small ODT. So what we can do, we can actually check what is the average number of arrivals, number of jumps in a given interval. So here we have used a shorthand notation, so you can see that we have a dxp, which is essentially number of jumps. So we have difference between number of jumps at point s plus dt minus xps. So this is what we substitute here. And expectation, of course, we have 1 because we have one jump times xpdt. So so as you know, the expectation is calculated by the expected value times the probability of an event. So we have two options: either jump happened or not. So if jump happens, we have a probability of that event is here, plus we have a jump not happening, it's 0, times probability, which is here, right? So this is, we substitute here, and we arrive at this expression. So this is something which also follows our intuition. If we have a specified interval time, we have certain intensity, which is psi p. On average, we will have psi p times the length of the interval number of jumps. This is also related to our diffusion process. As maybe you remember, I already have mentioned a few times. If we think about volatility, we always have a sigma squared of t. So number of uncertainty grows with a sigma times square root of time in Poisson process. And once we add jumps to the process, we will have a psi p times t. So you see, it is very much related. So we have an intensity of how often the jumps will happen times time. So larger the time, more jumps we are likely to see. Okay, what we can also do is that since we already have here, we have seen that expectation of a process xp is equal to psi pt. So this is something slightly different that we had for Brownian motion, because Brownian motion, expectation of a Brownian motion is 0. In this case, it's not. So what we can also do, we can correct for that term. So we can define xpt is equal to xp minus the expected value. And that new process, so xp t, is commonly known as a compensated Poisson process. So we make sure that expected value of this process is also 0. On the other hand, if we think if you consider stochastic differential equation, we have a dxt is equal to jt. So this is the intensity, the magnitude of a jump times dxpt. And we can also write it, so if you integrate those two sides, we can write it in the following terms. So we have left-hand side, of course, it will be, actually in this case, we do integration from t0 to capital time t, t0 to capital time t, and we end up with xt minus xt0 is equal to integral of this process is equal to summation of jumps, and we hear xpt, it is a number of jumps that happened. So as you remember, xpt tells us about how many jumps we had until time t. This is, of course, we have to count all the jumps with the certain magnitude, because it's not magnitude of 1. They have could be, even this jk could be a random variable, but we count all of those jumps. So this is the relation between integral and summation. Typically, we assume no correlation between, so if this jump magnitude, it's a random variable, here we have a process, typically we assume there's no correlation between the two. Otherwise, it becomes very complicated and practically also difficult to assess. How we would assess the magnitude of a jump and jump process, counting process. Well, as you can imagine, once you deal with market data and paths of a stochastic process, or let's say historical realizations, historical value of a stock, it's difficult to say when jump actually happened, because we have some discrete observations. So you have to make some decisions when actually, how you define a jump. So if we think of something, a correlation of something that we could not really define, that's very difficult, especially in this, when we consider here a continuous case. To summarize, we have here variable jk for k is bigger equal 1, so this jump is independent sequence of random variables with certain distribution. Later in this lecture, we'll discuss different types of distributions, and we have some we assume also that expectation of a jump, so the jump magnitude cannot explode. Otherwise, if the expectation would be infinite here, the whole process would be infinite, so that would not be very practical. So this is, you can think of it's a technical assumption regarding the jump magnitude. Okay, this is what once we simulate, this is what we get. So we, on the left-hand side is a process XP, right? And on the right-hand side, we have a compensated process. So you see that here we have an average, the average which is growing this way, and here the average is simply 0. So this is XPT, and here we have X hat PT. So the process which is defined here, it is the compensated version. So let us take a look how to implement this process. So how would you simulate the paths, how to simulate the realizations from this process. So here again, I have prepared a small piece of code. There are two parts of it. The first part, when you specify number of paths, number of steps, maturity time, intensity, which is here equal to 1, then we call a function with those parameters. And what happens here? So this is very much resembles what we have seen for Brownian motion. We define a matrix which will have number of rows corresponding to number of paths, number of columns corresponding to number of steps. This is here, we have compensated version. So we have two arrays, two matrices, whether it's a non-compensated and compensated. And what we do, we here define, before we had Brownian motion, we had simulated the independent increments, which were, we were simulating normal distribution, which was the distribution of the increments of a Wiener process, of a Brownian motion. Here we know that every increment are also independent, so all the increments are independent, and each increment is simply a Poisson distribution. So here we have the parameters for Poisson is xi-p, so this is the intensity plus dt. So if dt is big, we expect that this intensity, the parameter will be appropriately larger. And then what we do next, that we essentially, we go in time, but we operate on columns. This is what we already discussed. We have column plus column. So we don't make extra for loop for each path. We just consider that every column will contain all the paths that we want to simulate. So here we see that the process xi-p, this xp from an initial point. Of course, initially we knew that the value of a count process is 0, and then we add increment. We add the random variable which comes from Poisson distribution, and in the case of a compensated process, we take again the previous time step. This is like a discretization, and we have again the random numbers which come from Poisson distribution, and we compensate it by extracting minus xi-p times time dt times dt. And then once we plot it, you can obtain two. You will see two figures. The first figure is a Poisson process, and the second figure represents a compensated Poisson process. At this point, I would say this is very informative. That's what you see. Later, the element of subtracting or finding a martingale or making process to be compensated, it will be very much necessary once we talk about the pricing and measure changes once we deal with a Poisson distribution. So once we have learned how to define a Poisson process, we need to also know how to use it in Ito's lemma. Obviously, standard Ito's lemma is not considering a jump process in its dynamics of the stock. So now we need to make an extension to that. So let us consider a process given here. So we have a dxt is equal to a mu xt. So we have just a simple drift with dt. And then we have only the jump part. So we have a j hat t xt t minus dxpt. So we forget in this case completely about the diffusion part. We just concentrate about jump element. Our objective is to find out what is the dynamics for process S, which is defined for as an exponent of the process which is defined here. If you don't know what is this element here, it means a time just before jump. So it is formally defined in this line here. We have a limit s going to t for process xs when s is smaller than t. So we have a point t. We are approaching from the left until point t, but it's not there yet. So it's in the limit. So it is, you can consider that this t minus corresponds to the moment just before jump takes place. So as you can imagine here, you have a jump magnitude of a process which happens just before the jump. After the jump, it will be included in the dynamics. But later it will be clear what is the better intuition for this part, for this xt minus. So Ito's lemma for Poisson process is defined as follows. So if we have a function s, so actually here we can consider s is a function g of xt. So s is equal to that. So we need to find out what is dynamics for this. So with Ito's lemma, we always, if we have a stochastic process and we define a function with Ito's lemma, we are able to find the dynamics for that. So if we are looking for the dynamics for function g, we have something which we have seen before already. So the derivative with respect to time. Then we have very similar as we had in the standard ethos for diffusion processes. So we have mu times partial derivative of g with respect to x times dt. And now the most important element is the element which corresponds to the jump part. So here we have a g at time t where we have xt minus plus jump. So you see that's a comma, and this is whole thing is one expression. So this is evaluated at t with a value equal to the time just before jump, including the jump. So you can say, and here we have a minus. So you can see this function represents the difference between what happened before the jump and after the jump. How function g behaved. This is actually, this expression explains that. This is the difference. This is the difference of a value of function g before the jump. So actually after the jump minus before the jump. And then we have a dxp, which is a Poisson process. Intuition. So an intuitive explanation for Ito's formula in the case of jump is that when jump takes place, we have a dxp equal to 1. So we have a one particular jump. The process jumps from xt minus to xt. So this is what I explained. So we have just before jump, after jump. So we have only one moment when the jump could take place, with the jump size determined by function j. So this is, we already have seen, it's a j times dxpt. So j determines the jump size, resulting in the following relation. So this is actually the equality that we can see once we have jump. So we have a gtx is equal to gtx minus the minus jump plus the jump time. So you see that after the jump, so t is after the jump, we have a moment just before the jump plus the value of a jump. So this is a relation that holds. After the jump happens at time t, the function g is adjusted with the jump size, which is then determined at time t minus. This is the interpretation of this t minus. I hope it helps. In practice, we won't use this notation so much. In general, actually, we are not going to use jump processes heavily. However, it is important to know and be familiar with those derivations. If you have to derive a model which depends on jump processes, this is something that you have to keep in mind, how the Ito's lemma changes once you deal with a stochastic process is different than just geometric, than the Brownian motion. Okay, now we need to look further, because now in practice we are not going to have a model for stock which only includes drift and jump part, but we would also have a diffusive part. Keep in mind, of course, that we in this moment we work only under the case when a jump process, so this one, and diffusive process are independent. So this is kind of important. However, this condition is almost always imposed on the framework. The complexity once we want to include the correlation between jumps and diffusion, it's extremely high. So then the complexity is becoming the model in essence becomes difficult to derive if you like to have some solutions analytically. But once we have two of them, we also need to look how our ethos lemma needs to be applied, because then we also need to deal with a ethos table, and we need to look also at certain cross terms, especially if we think of a dxpt squared. So let's take a look. So ethos lemmas for function, the dynamics of g is then equal to partial derivative of g respect to time. Time, then we have a past drift, what we already have seen, first order derivative of g with respect to x. Then we have second, so we have diffusive part. So this part comes from this element. So we will have sigma squared second order derivative dt. But this is basically everything what we have already seen before from a standard ethos lemma. Other thing that we also have seen from ethos lemma, so this is known, this is standard. Also, we have seen this part, so we have a sigma derivative of g with respect to x. This is also what was given, and only part which is new, if we did in this framework, is part which includes jumps, and this is the part which we also have discussed as slides before. So you can see that once we put all these three elements together, then we arrive at the dynamics of function g in a model that we have jumps, and at the same time we have a diffusion process. Small extension that we have to incorporate is extension of ethos table. So ethos table, as you remember, it was table which involved relation between Brownian motions and dt's. So this is something that you already have, you are familiar with. Extension, it's related to the, of course, Poisson process, but since we assume, of course, independence, this part is rather straightforward. The only difference is that we have a dxpt times dxpt is actually equal to dxpt, and this is related to the variance of a process xpt, so the increment, and this is explained here. So we have a 1 squared probability because Poisson process in an increment of time can only take value 0 or 1. So if we think of a square, does not really change the values. So this means that we have a 1 with probability xi pt, 0 squared with probability 1 minus xi p dt, and this is exactly equal to what we had in the case of expectation of a Poisson process. So this is something to keep in mind, that if we have a Poisson process and we look at the ethos table, then the results change slightly compared to what we had in Brownian motion case, where dwt were equal to dt. So now let us return to the process involving a jump and also diffusive process. So now since we know how ethos lemma works, once we have jumps and diffusive components, we can come back to the ethos lemma and derive the dynamics for function g, which is s of t is equal g of xt. So this is this function. So by application of ethos, we have the following components. Once you see here e to power x, you can also consider this is equal to st, right? So this is actually by using the substitution here. So the dynamics for stock is equal to mu ext, so mu st, half sigma squared ext dt, and then we have a Brownian motion component. So this is something we have seen it already before for a geometric Brownian motion. We have a st dwt, and the remaining part is the element which comes from a jump. So we have here, you can see it's st times e to power j, right? So this is e to power x times e to power j gives us x2 plus j with a minus s of t dx pt. So if we divide the terms by st, which you see it will cancel out in many places. Actually, every term here involves st, also here. We end up the following. So we have mu plus half sigma squared dt plus sigma dwt plus 2 power j, which comes from here, minus 1 dxpt. And this is the dynamics of our stock once we have started with a process X involving jump and Brownian motion. So if we go back to our starting point, it was process derived here. So we started with a process with a constant drift, volatility coefficient, and a jump. And you see that actually once we arrived at, once we applied Ito's lemma to this, exponent of x, which is equal to s, we arrived at much more complicated expression that initially we could expect. So we have this term which is a little bit maybe counterintuitive, but it is what we obtained from the Ito's lemma. Keep in mind that this Brownian motion here is under p measures, so this is still something that we have to work on. So as we know that this process is, you can think of, is estimated based on some historical data. This mu component, it's not the one that we would get from interest rates. It is estimated based on some kind of econometrical models, for example. Of course, so the next step is how to, from this dynamics, how to arrive at the dynamics under Q measure. Keep in mind that we assuming independence between the variations. The simplest way to find the process under the Q measure, so under which we have Brownian motion, sorry, it should write a little bit better, nicer. Here, Q. So this is Q measure. It's when the dynamics of ST over money savings account is a martingale. This means that we are looking for mu for which this quantity is a martingale. And this quantity is a martingale once there is no drift. So this is something we have already discussed before. So our next step is to define a new variable y, which is equal ratio of s over mt, and mt is the money savings account. And we are looking for the dynamics of that process. First, of course, by simply substituting, we can see that dyt is equal to dst over mt minus rst dt mt. And we know that this quantity should have a zero expectation. This means that if you look at the dynamics should not include any drift term. So we know that this expectation of dyt should be zero. So if we substitute drift and Brownian motion, so we have an expectation of all the drift terms plus expectation of the volatility, we see that this part is zero because we have a Brownian motion there, and we have only left with the terms. This will be zero, and this term it corresponds to the jump part. So we have a drift part, we have a Brownian motion part, and we have expectation of a jump. Since our jump component, this one is independent of all other processes there. The same is for J. J, we assume that's uncorrelated to any other stochastic quantity. This is what we find. So we have an expectation of a mu st plus sigma squared. Is basically the same expression as we have here. Here we have an expectation. So this is our third term. So we know that's expectation of J minus 1 times st. And here we can take it, since we have independence, so dxpt is independent of others, we have a product of expectations, and we know that expectation of dxp, so we know that expectation of dxpt is simply equal to psi p dt, and it's the term that we see here. So, like I mentioned, this expectation is simply zero. So this is what we have here. If we go further, so we know that we have here mu. So, okay, let's take a look here. So we have two dt terms. So we have a one dt term here, one dt term here, there. And we have also common factor, which is st everywhere, as you can see. So we can take it outside. So we have expectation of st times dt. Then we have a mu minus, which is from here, plus half sigma squared. And now we have only one element left, which is an expectation of e to power j minus 1. And here, this xp actually can be also taken outside the expectation. As you can see, it here was already outside the expectation. Somehow I put it inside, but it can be outside the expectation. And now the question is when this quantity will be zero. This quantity will be zero if mu will equal to this term. So basically, the only one unknown parameter here is mu. So we choose mu to minus everything which is here, and that would guarantee that our expectation of a dy t is equal to 0. So this means that we can substitute the term that we have here. So you can see that before we had interest rate. So without Brownian motion, we had minus sigma squared with r, and now we have additional term, which is the correction term that we have to include in the drift to compensate for the Poisson process. So this is something related to what we have seen so far, that Poisson process itself is not a martingale, it's expectation dt. So in order to make it a martingale, we had to compensate. So this term corresponds to the compensating factor that we used in the process. So the term here is so-called drift correction term, which makes the process that we have a martingale. After the substitution, we see that our process now is defined under the Q measure. We have R minus xi p expectation of j minus 1. This is, of course, this is convenient here. That why this one is under the expectation. It doesn't really matter. dt, we have term which comes from diffusion part, and we here have additional term ej minus 1 d sine pt. This process 9 is often presented in literature as the standard jump diffusion model. So once you hear about the standard jump diffusion model, this is the model that it refers to. The standard jump diffusion model is directly connected to the following dynamics. So this is also what we have seen, we have actually started with, but we have started with the dynamics under measure P, not under measure Q. So you see, once you start with a process which is defined well under measure Q, to bring it to measure P, so to bring it from P to measure Q, it requires quite some effort, especially in ethos calculus and all those elements that you have to keep track of. Okay, and this is once we have generated, we have derived a model with diffusion and also jumps. Here's an example on how those paths of a model with two components, of diffusive components and jumps will look like. So I can see this is X process, and this is ST, which is an exponent of XT. So this is what we have here, and this is what we considered in ethos Lemma. So you see that there is a diffusive part, so the process behaves nicely, continuously, and there is this jump element which makes it discontinuous. This is something which resembles more reality. Of course, here I have chosen parameters such that it becomes clear that there is a jump. Of course, our jump magnitude, J, we have chosen to be normally distributed with mu J and sigma J. Of course, those parameters will need to be calibrated, and you could calibrate them using historical data or, for example, option prices. Okay, so I think there's no more slides here, but what we can do, we can take a look how to program this simulation, how to make those paths, how to plot those paths. So, and as before, we have three blocks. The first block here, it is about configuration, parameter settings, a number of paths, number of steps. We have parameters for jump. So here is the sigma j and mu j. This tells you about mean of a jump. So if there is a magnitude, what is the average magnitude of a jump? And sigma j is about uncertainty, how big jump will be. Then we have xi p, so this is intensity. We have a sigma, this is the volatility parameter for Brownian motion. We have some initial values for stock, and also interest rate. If we looked at the dynamics, so we have here the dynamics, which is, we see if we are using actually Poisson process. So you see this Poisson part can be removed. We don't use it anywhere. Yes. So for Mertens model. So this is also the standard model that I just mentioned. It's also called often Mertens model. So as before, we have X, empty matrices, empty matrix for S. And here we have, maybe remember, we had an expectation of e to power j. And assuming that j follows normal distribution, this is the expectation what we have. This is expectation calculated analytically, because we know that this process, this variable, it's a log normally distributed, it's e to power j, and this is the expectation of a log normal distribution. Then we simulate Poisson increments, which will be driven by Cp times dt, so this is the length of the time step. We have a z, which is increments for normal distribution, so this is for Brownian motion. And we have a j, which is another variable, so this is a jump magnitude. So as you can see that this j here, it corresponds to expectation here. So here we calculate analytically what the expectation of e to the power j is. Here we generate j as random samples from normal distribution. Okay, if we go to simulation, as before, we have some standardization element. This is not so much relevant, it is more for convergence. And now if we look at the dynamics, we have a next iteration step for process X is equal to the previous step times plus R minus xi p times expectation of j minus 1. So this is what we have, this expectation of e to power j minus 1 minus half sigma squared dt. And then we have a part which corresponds to the diffusive part. So we have a sigma times squared dt times random samples from random increments for normal distribution for Gaussian process, for Wiener process. And the last part is a j, so it's a jump size times number of jumps, which is a sample from a Poisson distribution. Once we simulate that, we can see that this is a process X. So it's a logarithm of S, which is here. So you can see every time we have a different set of paths. Some of them resemble, so if you look at S, it resembles indeed, there is a rather jumpy distribution. If we kill if we kill the volatility, for example, if you play with the parameters, so if we say, for example, sigma j is equal to 0, 0, 0, let's make it very small, then essentially we, as you can see, the jump size is removed, or it's extremely small, because it's a multiplier of a Poisson process. So once we make it very small, that doesn't have too much effect. If we make it large, if I make it, let's, for example, 2 here, see, you see that the magnitude of a jump, it's simplified, it's magnified. If we make a, oh, this is actually, you see, it's an exploding, if we have 2.3, it is super big. If 1.3, let's see how it looks. It's also extremely high. Let's make it like that. Yeah, so this is something that we have seen before. This code will be also attached to this lecture, so you can play with it. Of course, this is just illustrative part. At the end, you can see that we have number of parameters, and those parameters need to be calibrated. And typically those will be calibrated using option prices present in the market. Once we derive the dynamics of the jump diffusive process in the risk neutral measure, we can move a step forward and find out what is the actual PDE, or partial differential equation, for that pricing equation. In this case, actually, since we are dealing with jumps, we don't have only PDE, so it's a partial differential equation, but we also deal with integral differential equation, so-called PIDE. This integral part corresponds to the fact that our partial differential equation also depends on jumps. And that basically means that PDE will also involve integral, which is actually an expectation of a jump sizes that we have already seen. So as you remember, in the dynamics for the stock process under the jump diffusion model, so where we have a diffusion and also jumps, there's an expectation of a jump, an exponent of a jump -1, and that expectation makes it our pricing equation becomes PID, so integral part is also present in. Here we have two possibilities to derive the pricing equation for an option price. One possibility is by deriving a portfolio. So this is something that we have already discussed in first lectures. So by the portfolio, construction of a portfolio and replicating portfolio and hedging argument. So maybe you remember we first construct a portfolio pi consisting of an option that we sell. So this is why we have positive, because we obtain this premium today. And then we have a hedge with underlying stock. So by finding the dynamics of the portfolio, making sure that it on average increases in the same rate as the money savings account, we are able to find the pricing differential equation on partial integral differential equation. A bit simpler, and especially, like I mentioned before, more generic, especially if we deal with with high dimensions. It's a idea of deriving pricing equation via martingale property. As you remember before, to arrive at the dynamics of the stock under risk neutral measure, we had to make sure that the stock divided by money savings account is a martingale, and that gave us stock T under Q measure. Now we go a step further. So we are not interested anymore in the dynamics of S, because we already have it under Q. So this is what we derived before. So in a generic sense, so we have a dynamics of S is equal to mu, which is defined here. So you can see it depends also on S. There's interest rate R, and we have two components. We have a diffusive component, and also we have a jump element here. In previous few slides, we have derived what is the condition for mu such that S over M is a martingale. It means it's a martingale under Q measure. So it's a driftless under Q measure, and that gave us this dynamics. Once we have dynamics under Q, we can use this dynamics to compute the following expectation. So we use the same argument stating that not only value of a stock divided by money savings account, discounted stock value has to be martingale, but if we have an option discounted today also has to be martingale, and this is this equality. And in a next step, of course, once we want to find out what is the dynamics of V over MT, the dynamics would depend directly on a ST, but in order to calculate this expectation, we have to make sure that our ST is under Q measure. So like I said before, if we have an expectation with a measure Q, every element or every process that is used in computation of this expectation has to be under the same measure. So it's not allowed that if you would simply use mu here as a constant, which will be different than R, and you plug in to calculate this expectation. There has to be consistency in computation of measures. So okay, by Ito's lemma, actually here we don't need to use the extended version of jumps, because our value of the dynamics of our value does not explicitly depend on a jump process. So we can just apply Ito's lemma, which is the value of a derivative or an option divided by money savings account is equal to 1 over m dv r minus r v over m dt. And for v, we do what we have done before. We derive the dynamics of v, and we know this dynamics of v, or we can derive it because we know that v explicitly depends on the dynamics of a stock. So by Ito's lemma and substitution, we can actually find out the following dynamics of v. So we have a drift term, and we have also elements which come from the dynamics of stock. So we have a diffusion term, and also we have a part which is responsible for jumps. So of course, once we have this element, we can substitute this to this equation, and this stays the same. So we can continue on. As you can see here, we did also a substitution. So our v is a function g. This is, if we apply Ito to g, then we essentially apply Ito to v. And then we also use j bar, which is equal to es minus 1s. So this is just for simplification, so that equation fits the slides. So in order for this quantity, d over m to be martingale, we know that this dynamics of this whole process needs to be equal to 0. So this means in expectation should be 0. So this means that if we take this term, of course, it is an expectation is equal to 0. So we are only left with 3 terms, the dt term here, and we also have a expectation of this term needs to be 0 too, right? And this is also dt term. So if we substitute, if we basically take 3 elements here and take expectation, then we end up with a drift term here. Then we see that, so this term is taken here. Then we have a minus RV. This term is also included here. So you see that put together. And now we have an expectation of a value of derivative, which depends on a jump size, minus v of ts. This is also known. This can be taken outside the expectation. Actually, it will be just a vts. And we also have an expectation, which corresponds to this term, of dx p under measure 2. And we know that this expectation is simply equal to psi p. So here we end up, of course, will be minus v psi p with minus rv. If we collect all those terms, we arrive at the following equation. So we have first order derivative of v respect to time. Then we have it's also first order with respect to s. We have s here. We have expectation of e to power j. Then we have diffusive term, which comes from the Brownian motion. Then we have 2v, which depends on interest rate, and psi p. You can actually see this is some kind of compensation. So we have already presented that because we deal with Poisson process, this compensator, so that Poisson process is a martingale, it needs to be present also in a drift. And we also have an additional term, which is an expectation of a value of a contract at time t, and then includes a jump. So you see that our expression here involves an integral, and actually it depends on distribution of j. So if a jump magnitude of a jump is stochastic, then we need to solve this expectation. Of course, in the simplest case, once we just say that j is constant, that's trivial. But in a generic case, when we say j follows a distribution, for example, normal distribution, then these expectations, they need to be solved too. To summarize, once you have a PDE which involves some expectation, then it's not anymore PD, then it's a PID, then it's a partial integral differential equation. So this is something to keep in mind. Whenever somebody says we have a PIDE for pricing, you can immediately think of a jump that is also included in a model. Like I just said before, we deal with a partial derivatives. The expectation gives rise to an integral term. PIDs are typically more difficult to be solved than PDEs due to the presence of additional integral terms. So of course, as you can imagine, if you discretize this expression, then every time you need to calculate an expectation depending on the realization of your S. And obviously you need to also know the distribution of your J that also would affect the expectation. So every time you have to solve some numerical integrals. An analytic expression has been found. So those expressions for expectations, they exist in a case of a model of mergence and models of Q. And those will be, in particular, I will discuss later in this lecture when explicitly the density for J will be given. And then we can find the analytical solution for prices of those options, and those will be given in terms of infinite series. So once we have, so in general, in this case, we haven't specified the dynamics or the distribution for J. We just say it is a random variable. This is why we also have this generic expression for an expectation. Once J is specified, in some cases, we can solve this expectation in terms of infinite series. To summarize, of course, once we have a PID, to solve this PID, we still need to have a boundary condition or terminal condition. In this case, you see that now the expectation is replaced with an integral. So an expectation and integral, they are equivalent. So you see that we have an integral over value of a derivative of our option with respect to density. So here, this density, it will be simply, as written here, it is a density times dy. And we have a terminal condition which says at the maturity, we have a maximum and depending on alpha, we have either put or call option. So this is a summary. We can also transform our PID into log transformation. So from numerical perspective, it is sometimes more efficient to perform a logarithmic transformation, which essentially means we linearize our problem so that the convergence can be better. Under PID, and PID under the log transformation is given as follows. So we will have some additional terms, like for example here, for the drift, and except for that, it does not really change so much. So except that our payoff would depend on now explicitly on x plus y, and instead of multiplication with j. And again, terminal condition is specified as either call and put. In general case, it can be other payoff, which would depend only on the terminal payment, which will take place at capital time t. So if we have paths, or if you have payoff that would depend on paths, then this would not hold anymore. We need to think of different methods. But this case, we're still focusing on smile aspects. So we have only considered payoff that happen only at one given particular time. The specification of a jump magnitude j, it is essentially up to you. You can decide which process or which distribution is the most suitable for your purpose. However, there are two common approaches. The first one is a classical Mertens model, which says that a jump should just follow the magnitude of a jump j, should just follow normal distribution. And this is typically enough. As you can see that once we define j to follow normal distribution, we introduce two additional parameters, mu j and sigma j. And already at this point, I would say the calibration of the model becomes much more complicated. So instead of having just a sigma, we also have then a sigma j and mu j. So it should be a mu j. And that complicates already significantly the calibration part. So you have to really think carefully how to do it. In general, having three model parameters is not so much. Hopefully, it is enough for you to fit the smile. However, in jump models, typically there will be a strong interaction between the parameters, so they are not really separable. They are not independent. This means that if you have a smile or skew, both parameters could give you very similar effect, and that's something that you may not wish to have. On the other hand, we have also alternative. We have a model of Q, which is so-called non-symmetric double exponential. As you can see, depending on x, we have two different regimes. We have P1, alpha 1, those are constants, and we have some exponential decaying function, and the same here, but this is actually increasing, of course, depending on the parameter alpha. So this is also alternative. For these two models, the PID, or the pricing equations, are known in closed form in terms of infinite sums. So this is something that you can consider. Here, of course, in this case, we have one more parameter. So we have a P1, P2, but also we have alpha 1 and alpha 2 that need to be specified. Personally, I don't, from my experience, I did not really see a big benefits whether we switch from one model to another one. Typically, a jump is not something that you really you concentrate so much on. So typically, the simplest jump model that you specify, it's already enough. And I would say by switching to different models, you may benefit, but typically it is a benefit that you cannot really measure. The biggest problem, of course, with those models with jumps is that if your dynamics, your distribution for J is too complicated, then it's much more difficult to achieve the convergence, proper convergence. And on the other hand, if you simulate, for example, instead of PD, you perform only Monte Carlo, once you think of a calibration of a model, this becomes also problematic if you have only Monte Carlo engines. So then you need to use some more advanced techniques like Fourier space or even analytical solutions to calibrate those parameters. So the bottom line is that if you have a feature of a model that you like to preserve with as few parameters as possible, that's great. So if you have few parameters and you get to your target of fitting of the model and having also proper hedging parameters, that's excellent. However, if you fit your model excellently, but you introduce additional 10 parameters, that's very impractical and often would be rejected by the industry. Typically something that's simple and works, not perfect, that's more accepted than something which works excellently but is extremely complicated and very expensive to simulate and to perform pricing. We can also use so we had discussed already PID, but if we apply a Feynman-Katz theorem, so a theorem that we already discussed before, we can also perform pricing given just Monte Carlo simulation. So also in the previous parts, I presented to you how to perform simulation of a jump diffusion process. So this means that it's expectation, maybe you remember it was expectation of e to power j. This is for models that we discussed, it's known analytically. Then you can also perform simulation of your process for S, the stock process, using Monte Carlo. And then you can perform the expectation, computation of expectation using just a Feynman-Katz theorem. So you just discount future value of your future payoff. So value of your future payoff, you discount to today, and that would also give you the price of a derivative today. What to add more? I think it's at the end, if you think from the computational complexity, if you have a method like PIDs when you discretize, or you have Monte Carlo, those methods perform very well. Once you talk about pricing, they are typically not very good once you talk about model calibration. So as we already have seen here, once you introduce jumps in the model, you have parameters corresponding to distribution of J, but also you have xi p. This is the intensity parameter. So this means that number of parameters increases significantly. And that's questionable. Not always people wish to have a model with so many parameters. And so typically something which is simpler but works, it's much more acceptable. Later, we will discuss models with stochastic volatility, which have fewer parameters, and they are much more independent. It means that each parameter would correspond to particular behavior of implied volatility, smile or skew, and that's typically something that industry prefers. So here's another example, just two graphs, the one graph representing just a Brownian motion, so diffusive model, and here we have diffusion with jumps. So as you can see, on the red line indicates the size, the magnitude of jumps. So if you think of a jump, you can see, okay, this is magnitude, this is magnitude, this is magnitude, this is magnitude. This also shows you about magnitude, and so here we could say J, for all of those black lines is J, and the distance between them, so if you look at average distance between those jumps, then you think of xi p. So this is how to think. So xi p determines how often, J determines how large. So of course, if you have J, which is constant, then you would expect that every jump that happens would have the same magnitude. On the other hand, you see that it's a short, big, small, small, smaller, very big. So if you can actually look at the distribution of those J's, these sizes of jumps, maybe at the end, in this case, if you do it, if you simulate a large number of jumps, then you could see that this is actually distribution of J. So this is normal distribution. So for example, this distance was here. This one was, for example, here. Then we had here, a small one. And if you would plot a histogram, very likely this kind of shape you will get. And intensity tells you about spacing, how often. So if you have if stock is particularly not dependent on market fluctuations, but only if the market crashes completely, then it crashes, then you would expect that intensity is not so large. If you expect that jumps happen frequently, then intensity parameters should be rather large. Finally, we can check what is the impact of jump parameters on implied volatility, smile, and skew, because that's our ultimate goal. Once we specify the dynamics of a process and we extended the model, the Black-Scholes model, with additional jumps, the question would be how much we have improved, how much control can we have over jump and skew or implied volatility effect in general. So in this slide, we discussed this effect. So we have defined J, so the jump element, magnitude of jumps, to be normally distributed with mu J and variance sigma J squared. And now we will perform the following experiment. We vary one of those parameters while the other parameters are fixed. Okay, so let's take a look. So let me zoom in the graph. Oh, sorry. So we can see that volatility of a jump has effect on curvature. So we see there is a much more smile effect or flattening of the smile, and also level effect. So by increasing of sigma j, so the uncertainty volatility of a jump magnitude, if volatility increases, then the overall level increases. But this is what we expect. If the jumps are large, or magnitude of jump is large, this means volatility is much higher. This means that we would expect that the smile or implied volatility shape is moved upwards. Once the sigma j goes to 0, this is also what we have seen in our simulation, then you would expect that the model will converge to Black-Scholes equation because the magnitude of jump goes to 0. Now, the second one is the intensity of jumps. So very similar effect, maybe not so much pronounced when we talk about smiles. However, also intensity of jumps has also impact on level. So once we have more intensity, this means jumps happen more often. That increases the volatility. But that also makes sense. If I have one jump of 1, or I have 20 jumps of 1, this means I have 20 times more volatility. So this means that contribution, once I have a higher intensity, it means I have a higher volatility. Mu j is a bit different. So you see there is a different shapes of mu j. Of course, the most neutral is around 0. So it's basically somewhere around here, because that means that jumps are symmetric. This is the case once the jump's magnitude it is normally distributed. So we can also have negative jumps, so the downwards or upwards. And we see that if there is a bias towards up or down, then so in the upward, so if you have a positive average or mu of j, then the implied volatility smile looks as follows, or we have downward. So you see that that's kind of weird. We would not expect in reality to see such shape. So you see that there is a lot of interaction between the parameters. If I would give one of those graphs, it would be very difficult for you to find out or to explain which effect we are actually seeing. Is it effect of a sigma j, psi p, or this is mu j? And that's one of the limitations or problems with jump diffusion model, that it's difficult to separate the effect of different parameters. This means that in a calibration, we cannot fix any of those parameters. They always have to interact with each other. When dealing with jumps and computing expectations, sometimes it may seem very difficult. In this part, I would like to discuss the conditional expectation and Tower property for expectations to handle jumps and integrals, including jumps and summations. Okay, let us take a look. So first of all, we start with random variables xi. So we have independent random variables with mean mu. Then we have nj, which is non-negative integer valued random variable, independent of xi's. Now we would like to show the following expectation. So we have an expectation of a sum from I to nj, and nj, it is a random variable of random variables xi's. And that's so-called Wahl's equality, which says we will have this expectation is equal to mu, and mu is an expectation of x, times the expectation of jumps. So as you can see here, we don't really rely whether it's a Poisson or another equation. It is basically kind of counting process or counting random variable that we have. As you can imagine or actually as you have seen in the lecture, the integrals, especially involving jumps, is typically associated with a stochastic differential equation, including Poisson for jumps. So that basically it's a one-to-one correspondence. So let's take a look. So the method that we will be using is a Tower property for expectations, and this is how it's defined. So first of all, let's see that expectation of x given y. This is property what it says is equal to an expectation of x. So by conditioning expectation, we may actually, the expectation inside, the inner expectation, it's often simplified because expression which would depend on y, it is deterministic. So we can simplify and we can handle it easier. The example would be given here. So we have an expectation z condition on z2, which basically would be equal to, so we have outer expectation of z2, so a probability of z2 equal to z, and the inner expectation of z1 condition of z2 is equal to z. So this is basically the inner part. It is given here, times the probability of z2 equals to z. So because then we have to solve the outer expectation, and since we deal with discrete random variables, we have summation of all the outcomes, and we multiply with probability the particular outcome will happen. So if we go back to our equation, then we have expectation of summation of all x k's until nj. By conditioning, essentially you can see that so we have two random variables, we have xk and we have nj. By conditioning on nj, we can separate xk and nj. So one of them, nj, actually will be deterministic given the condition. So this is what we have. We have summation. So this is the outer expectation of the inner expectation, which is here. So expectation of a sum of xk, given that we have only a fixed number of jumps, elements in the sum, times the probability that the number that we use here is equal to n. So you can see that we go over all the possible number of events, and we perform this conditional expectation. Now this will be equal to the summation of n equal to 1 to infinity, and then we have a probability that, so this is a scaling, so every time we look at what is the probability that we will have particular number of events, so this is this probability, times, and then we exchange expectation with summation, and we have a summation of expectations of xk. And if we go further, we know that expectation of xk was equal to mu, so this is what we have. So this means that mu can go outside the expectation, and then we end up with so it's actually n times mu, right? So number, if you sum mu n times, you have n times mu, so mu goes outside the summation, and here we have n times probability of nj equals to n, and by definition this is mu times expectation of nj. So this is the proof for the Wahl's equation. So I find it very handy, and often in computational finance, in general in finance, often by using Tower property, you can simplify your problem to deal with. As we have seen here, is that by conditioning, our inner expectation become much simpler. For example, we can see it here, that did not depend anymore on nj. So it was just a summation with a fixed number of elements that we summed. And then we just scale it with probability that that was really the case, that we had that many elements. And especially often when we have multiple dimensions, so 2-3 dimensions of stochastic differential equations, that is very beneficial because we can condition on a path from one process to compute expectation or price of another process. To simplify, you can also think of a Black-Scholes equation when volatility parameter, for example, is stochastic. This means that for every realization of sigma, you'd basically have a Black-Scholes equation. And then if you like to compute the option price, you will need to multiply probability of a sigma event. So basically you randomly choose a sigma from a sigma distribution, from volatility distribution, and you scale and you basically sum over all the outcomes, and you multiply with probability that this is the outcome from the distribution. So then you can also do that in Black-Scholes model simply by taking multiple outcomes of the, let's say in this case was volatility parameter. And here we have an application, as I already mentioned, in once we talk about SDEs with jumps, integrals often become summations, especially if we have counting processes. So here we can also apply the same property once we calculate an expectation of xt. So this is actually definition of a Mertens model. So under Q measure, we have two elements. We have a Brownian motion, we have a jump, and we can compute expectation of this whole expression using the Wout's property, so the one that we have just discussed. Of course, everything would depend on our assumptions, right? So we have assumptions regarding jk, and then also we have a parameter xip. So xip, it is actually defined here. So this is the one element of the Wout's equation. We have expectation of xp. So it's a Poisson process. It's simply xp times t. And then we have a expectation of jk, and that's basically given. We assume it's finite, and that's mu j. So far, we have learned that once we have a stochastic process which involves diffusion or jumps or even both, we can solve the equation, the pricing equation, either with Monte Carlo. Of course, we didn't discuss so much in detail Monte Carlo techniques yet. Those will be discussed later. But you can also derive PIDE or PDE equation. So with Monte Carlo, we can solve using Feynman-Katz theorem. PIDE, we can use it according to the martingale approach, for example, if we derive the pricing equation. Another way of solving a pricing equation is with Fourier techniques. The advantage of Fourier techniques is that it allows the computation of pricing extremely fast. So once we think of Monte Carlo, we always think of simulating some Monte Carlo paths. If we talk about the PD discretization, we discretize certain grids. However, those methods are not very fast, and speed is very important, especially once we talk about model calibration. Then each model evaluation, it has to be really performed in milliseconds. So as you can imagine, it will be difficult to achieve millisecond results using Monte Carlo or PD methods. So in this section, I will introduce you. This will be slow. We will move towards Fourier techniques. Fourier techniques always depend on a characteristic function. So it is not straightforward in the sense that for Black-Scholes equation, we could find pricing equation using density. However, if for more complicated models, also including jumps, density, it's not known, or it is too involved and it's too complicated to find it. Or, for example, density is given in terms of some partial differential equations, for example. It also can be the case. However, in some cases, and also this is what I will discuss today, it is possible to find a characteristic function, although the density is much more difficult. So this means that in some special cases, we are able to find characteristic function in analytical form. However, for those, we will not be able to do it analytically if we think of a density. This means that if we have a characteristic function, then we can use it for Fourier techniques. So let us take a look closer. So we have here we consider a Mertens model, so something already we have discussed. We have a drift, which is defined here. As you can see, a drift is just a constant with interest rate, volatility as some expectation. We have a volatility part for the diffusive part, and also we have a counting part for jumps. So we have at jumps, a number of jumps is according to Poisson distribution. Okay, the question is how to find the characteristic function for this equation, right? So how to find characteristic function for xt. Using definition, characteristic function is defined as follows. It's an expectation of a iuxt. So this is an expectation, and we have a complex plane of argument u, and then it's xt. By substituting the previous equation, so by substituting this expression, we arrive at the following expectation. So we have two expectations. So we have some constant part that we can take outside the expectation, plus we have a product of two expectations, one involving Brownian motion, Wiener process, and second involving jump part. As you can see, we separate the expectations because we assume there is independence between Brownian motion and the Poisson process and jumps. We know also that since Brownian motion has follows normal distribution with mean 0 and variance t. Expectation of this expression here, it is given in closed form. It is an exponent of minus half sigma squared u squared t. For the other term, for this one, we can use actually Wald's equation that we have just discussed. So in this way, we can actually express by conditional expectation, we can find the summation, the expression will be summation of expectation, inner expectation, times the probability of number of jumps, which can be further simplified as follows. So we have a summation of e to power exponent I, u, sum until n, j, k, and we sum over all the n's. And since, of course, we have an expectation of exponents with summation, in essentially it means we have an expectation of products of exponents, which are basically all of those exponents are the same. So this means that we have an integral here, e to power I u x. So integral is an expectation times the density of j, because this is what we have, times 2 power n. So this comes from this term here. Now the next step is about the summation. So we see here that we can actually include xi pt under this integral, under this bracket, because we see that xi pt to power n is also power n here. We can include under this bracket, and we have the following expression. Now we realize that actually the whole this term, it resembles very much definition of exponent, where we have a summation from n from 0 to infinity. Here we have x to power n divided by n factorial. This means that actually here we have n factorial. This is basically our x. So this is how we can think. So after substitution, and also including this exponent term, in terms here, we can see is actually here it's a -1. This is the expression what we got. So we have a xi tp, and we have integral, and then we have, of course, we can also put under integral, we have an integral over fj. Of course, the tricky part here, you just, not tricky, but maybe something you can easily notice, density, integral over density of j of x is equal to 1. So this is why this 1 is included under the integral. And this also is a definition of an expectation. So at the end, characteristic function is simply exponent of xi pt, expectation of e to power I u j, and then -1. And this, although our characteristic function looked very much involved, you see that this is actually, so we have some constant terms here, constant. This is also given explicitly, although everything started very much complicated, but because we have used the conditional expectation, the Tower property, like I said, it's very, very handy. We arrived at a very nice closed form expression for characteristic function. This characteristic function later will be used in evaluation in the Fourier once we'll be talking about Fourier techniques.